Okay, so now we're going to be using another recording system which is going to capture the screen, and you're going to see a lot better what is in the screen and what is in my notes, and it should be just one file instead of 3 or 6 as we had before. All right, so let me ask you, did you guys start working on project number 2? No? Some of you already did, and some of you didn't. We are catching up with 1 week that I wasn't here. It's my fault, right? So if you need more time, just let me know, okay? There are some of these topics that may be totally new to some of you and not that new to many others. So if you need more time, just let me know. But we have seen all the theory that you need in order to solve problem number 2. And probably if you need a little bit of help with plotting, remember that the charging is available. Send you an email and he'll answer. And I'll ask him about office hours every week, but I keep on forgetting that. I'll try to do that and remember that. But you should know everything that you need in order to solve this one. And because you know everything to solve this one, we'll go to the next one. And I forgot to print out copies. I'll try to have them on Wednesday for you. And this is project number 3. And for this project, the objective is to build what is known as a one-dimensional mechanical earth model, which predicts horizontal stresses with the theory of linear elasticity. Many people argue that this might not be correct at some points and may not be super accurate, but still it's a very good exercise to understand what is the variation of the stresses as a function of depth and as a function of the mechanical properties of rocks. So basically for this problem, what we're going to do is we're going to, let me go back in here. We're going to utilize this file, which is a file from a well log, and in this file we have depth, we have pore pressure, we have density. You already know how to deal with that. You already know how to compute vertical stress, density, depth. You have everything you need. But in addition now, we have 2 other properties. We have compressional wave velocity and shear wave velocity. Those 2 depend on the mechanical properties of the rock. And we can utilize the theory of linear elasticity to combine those 2 measurements and calculate a Young modulus and a Poisson ratio. So with these 2 velocities, or in this case slowness, we're going to build a mechanical model of the subsurface. For example, when the slowness is very low, like here, or actually, I just want to tell you that you're not going to be able to see the pointer in the videos. Okay, so there's a point in which just if you help me remember that I'm pointing with the mouse, just try to remind me to not do that. Here, between depths of 18 to 1900s and between depths of below 2400s, there is a small slowness time. That means that the wave goes very quickly compared to this region. And what that means is that the rock is stiffer in these regions with a low travel time. Based on that, we're going to tell how stiff are the rocks, and based on the Young modulus and the Poisson ratio, and using the theory of linear elasticity, we're going to tell what are the horizontal stresses, assuming that we have a tectonic strain due to the movement of tectonic plates. So that's the direction in which we are going. And we're going to need quite a bit of theory in order to get there, but hopefully we're going to finish in 2 or 3 classes. Still, you can start working on this file, download the file, start making the plots of density, slowness. You can compute total vertical stress, something that you know, and then later we'll add the horizontal stress. Okay, so then let's see how we get to the solution of this problem. Yes, Stefan, welcome. Not at all. Not at all. You can do everything in the metric system. That's fine. Yeah. Yeah. No. Sometimes in the undergraduate course I ask them to do both because I want to know both. But if you want to use metric system, that's fine. Yes, definitely. Okay. Yes. Okay, that's a very good question. We didn't get much in there, and probably I didn't mention that, but remember that I'm asking you also to read these notes. And here in the chapter of stress and faults and fractures, if you go to applications, and if you go to critical stress, fracture, and permeability, you will find a description of, let me see if I find a good one. And that's the other one. Okay, let's just going to use this plot. There is a theory that in brittle rocks that are closer to shear yield, those are more hydraulically conductive. And that tends to be true mostly in brittle rocks, like for example granite or carbonate rocks. If the fractures are closer to shear and are practically shearing in a very long time, because of the ongoing shearing process, those fractures will usually tend to be more open than others which are somewhere over here. That's one of the theories proposed by Mark show that fractures close to shear yield will be more hydraulically conductive. In some places it doesn't hold, but for brittle rocks, most of the brittle rocks it does. Yes, Jack. Lesson is what? Oh, okay. I think I see what you mean. So you refer to this case. So if in this place, if you compare the case with minimum horizontal stress going in this direction on the right case, another fraction will tend to go perpendicular to the least principal stress, so those three planes coming out from the screen. Perpendicular vertical. And it's already agreed on the direction of, in this case, SH max, then if you get the vector in these regions as the vector set to operate, the vector in the same plane. And because the vector in the same plane, they're going to connect to each other and just form a large hydraulic fracture. That's not necessarily what you want. What you want is more surface area, more fractures out of the same gather. Alright, so let's talk about how we're going to use how we're going to use continuum mechanics to solve a general problem. So this is a general solution to a continuum mechanics problem. And this is going to be a general solution. The case that we're going to see for predicting horizontal stresses in the subsurface is just one simple application out of this. But with this theory, you could solve any problem of stresses and strains in a continuum. Alright, so in order to do that, we are going to use, and we're going to need three equations. And those three equations are, first, the most important equation, which is the equilibrium equation. If you remember, we derived this equation and tells us that the summation of forces, which is basically stresses, is equal to mass per unit volume times acceleration. So this is second Newton's law, and it's just basically equilibrium. We have this, and we put a name to that, and derive those equations, which is Cauchy, and those are the Cauchy equilibrium equations. Remember, this is just force or stress equal to mass times acceleration. Okay, that was the first equation. The second equation that we're going to need is an equation that links strains, because when we put a stress on a solid, it's going to deform. And that deformation in mechanics is caused by the term strain, and we're going to need an equation that tells us what are the strains as a function of, let me use another f, just to be clear, it's not the same f as a verb, as a function of displacements. If you know how a solid displays in 3 dimensions, with this equation we're going to be able to calculate deformations. And we're going to see an example of this in just a bit. These are called the kinematic equations, where from Greek, kinos or kines, I'm not sure, means movement. Now, these are the equations that relate movement to strains, or displacements to strains. And the third equation that we are going to need, it's an equation that links stresses to strains. So if we know the strains, we can tell what the stresses are. And this equation bears the name of constitutive equations and depend on the properties of the materials. The first two, they don't. The first one is equilibrium. It's valid for anything. The second one relates displacements and strains. So it's also valid for anything. And the third one, it tells you how much stress you're going to get from deforming a solid a certain amount. And that does depend on the properties objective is going to be to calculate stresses as a function of strain. So now I know that this is going to be a stress, and that stress I want to put it as a function in this equation, right? So now I have a stress. This is going to be the gradient of this term, the divergence of that term, and this is going to be still the same. But now I know that I can calculate strains as a function of displacements. So at the end, the equation that I have to solve is an equation that goes back all the way to solving displacements in order to solve this mechanical problem. So at the end of the day, this is going to be our unknown, and this is what we're going to solve for. So this is just an equation with things that we know and things we don't know. Many cases we're going to see that set the acceleration equal to 0. That means that inertial forces are very small. And for example, these are the body forces, something that also usually we know. For example, gravity. And our unknown is going to be the displacement. If we solve the displacements, we can tell what the strains are. If we know what the strains are, we can tell what the stresses are. And that would be a very general solution of the continuum mechanics problem. Just with these statements, you could solve any problem, any weird material with weird deformations, you could solve it, okay? But now we're going to make a simplification in order to solve this with a relatively simple solution. And for that, we're going first to assume one case out of kinematic equations. In general, you can have kinematic equations for small strains and for large strains. Those are two cases. Those are two cases in which you can write these equations, these kinematic equations, for large strains or for small strains. We're going to see the case of small strains, which are a little bit easier. But there are some problems, some very important problems that require formulations with large strains. For example, if you want to model the how a salt diaper moves over millions of years of time and how it rises and goes through sediments, probably you need large strains. Okay, you cannot do that with small strains. If you want to model how, like, this bottle crashes and deforms like this, you need large strains. You cannot do that with small strains. But for problems in which the formations are very small and displacements are also small, you can use the theory of small strains, and that's the one that we're going to see. And before I go into those ones, just to close the loop here, in constitutive equations, we're going to have several types of laws, and one of those, and the simplest one, is going to be linear isotropic elasticity. And this is the one, these are the two ones that we're going to use to solve this equation over here. Still, we're also going to talk about another type of model which is a little bit more complex, like orthorhombic elasticity or transverse vertical isotropic elasticity, and later on we're going to add to the elastic part plasticity. So all of that is going to go into this part, and that's going to tell you how the material reacts as a function of the deformation. This is transverse vertical isotropic, or also goes, I always forget because I don't know if some people call it differently, or it also goes by VTI, vertical transverse isotropic solid. We're gonna talk a lot about this because this one is closest to rocks. Linear elasticity is not. Isotropic is not. Orthorhombic sometimes, but too complex. This one is the one that gets closest to rocks, and we're going to talk about that. Very likely not today, but hopefully on Wednesday. All right. So equilibrium, we know that. Checked. Okay. Let's go with kinematic equations. And after we do kinematic, we'll go with the constitutive equations. Okay. So let me continue here. For kinematic equations, again, we're going to adopt the derivation for small strains. Let's first define what is a deformation. Let's imagine that we have a bar that we can assume as a one-dimensional object because it's a lot longer in one direction compared to the other two, that we subjected to a force. So let's idealize that bar just as one line in an axis that goes from the beginning to the end. Okay, so at a position or at the time t equal to 0, let's say that at some place in the bar I am at the position x, and in a segment of the bar over a distance dx I reach to the other point, and we know where those are. The first point is at x, the second one is at dx. You could also say that this is the origin and equal to 0. But this is at time equal to 0 before applying a deformation to the bar. Now we're going to see where those points go after applying the force. And let's first project those 2 points. If this is an elastic material, this is going to stretch, and this point is going to move somewhere over here, and this other point is going to move also somewhere over here, but because it is stretched a little bit more, it's going to be a little bit further, somewhere over here. So let's see how we can define the new positions based on the original position. All right, first we're going to say that the first point move a quantity u, where u is a displacement. X is a position, u is a displacement. Okay. Now let's see. The new position of this point is going to be x at time t, and the new length of the stretch bar is going to be dx, but now at time t as well. And if I were to project
the original length dx onto the new length, I'm going to find, let's say that from here to there, that was, I'm going to throw a parallel line to this one. This additional stretching is what I'm going to call du, is the additional displacement within this section. So with all these quantities, now I can use them in order to calculate what is the strain. And the definition of a strain is going to be that it's the change of length divided the original length, right? So we all know that, and if I just write that, that's going to be the length of the segment at time t minus the length at time 0 divided the length at time 0. And if I write what are all of these numbers or these quantities in terms of positions and displacements instead of lengths, I'm going to get the following. So let's write the first one. The xt is going to be that position, which is, in order to get to this point, I need first to get to x, then I need to add u, then I need to add dx, and then I need to add du. That's, in terms of position, that point over here. And then I need to subtract that to the original, to this point over here, this position, and this one is basically x plus u, and this is going to be this length, dxt. The initial length is a lot easier. It's just x plus dx minus x, that's dx, and we can already see that, well, but let's write it anyways, that's just dx. All right, so this x is going to go away, that one is going to go away, this one goes away. Notice over here, we have, yes, Jack, thank you very much. This is just x. So that x goes away with that one. Notice here we have xu and xu. So these two are going to go away. And here we have dx plus du. But here I have a negative dx. Here I have a positive dx. So those two are going to go away too. And at the end of the day, the equation I'm going to get is that the definition of strain, or the result of strain, is going to be du divided dx. Which, in mathematical terms, it tells me that this is the gradient of displacement as a function of position. It tells me strain is basically how much displacement changes for a change of position. And for one dimension, this is what we recover. So du divided dx, and it kind of makes sense, right? Graphically, you can see that the change of length is du, and the original length is dx. This might seem like an easy example, and more or less it is, but I want to save time because I don't want to do the demonstration in 3 dimensions, because in 3 dimensions it gets really a pain, but it's exactly the same thing. but in 3 dimensions. In 3 dimensions, we're going to have 1, 2, 3. At a given time, you may have a point at the position x, where x is now a vector, and after some time, that point may move with the displacement u, so the new position is xt. And you can apply exactly the same concept and derive from here the strains in 3 dimensions, something that we're going to call the strain tensor. And the strain tensor is going to be very similar to this equation, but now in 3 dimensions. It's going to be the Jacobian of the displacement as a function of displacement. So before I write that, how many components does the vector u have? Three, right? u1, u2, and u3. How many components does the position vector have? Also 3 components, because those are just vectors. And the Jacobian for this matrix is not going to be exactly equal to the strain tensor, okay? But we're going to get it from there. So I'm going to say that from the matrix I'm going to write, we're going to get a strain tensor. But it's very similar to this equation, and the equation is going to be the variation of displacement 1 in direction 1, variation of displacement 1 in direction 2, variation of displacement 1 in direction 3, and so on. So now, before we just had one change of displacement as a function of length or position, because we had 1 dimension. But now we have 3 displacements and 3 directions. So I need to consider all of those changes of displacements in all the directions. It's very hard to write something and speak another thing at the same time. So if you see any mistakes in my handwriting, please let me know. At least for me, it's very challenging to do that. Okay, this is what is called a Jacobian matrix. Okay, so we're almost there, but not quite yet. So let me see. Okay, I'll come back to this page. What we're going to do next is going to require an entire page. So also, if you want to start a new page, please do that. But then I'm going to write something in the previous one, so we save that space. All right, so let's try it again. The Jacobian. Okay, I need to keep an eye on this because I think it's going to log off automatically at some time. Let me know if you see the warning sign. Okay, I'm almost done. All right. Let's start with the easy one. We're going to decompose this Jacobian in 3 parts. The first part is going to be the elements in the diagonal. So all the off-diagonal terms, I'm going to make them equal to 0. Doing an analogy with the previous equation, if we have a change of displacement in direction 1 compared to a change of position or length in direction 1, the result of that is going to be what is called a linear strain. And if I want to put it in graphical terms, it's going to be this. Imagine that we have the cube with which we work all the time, with the third axis pointing here towards you. And we have the cube, and if I have a change of length in direction 1, and only in direction 1, the new shape of the cube is going to be that. And we can interpret the change of displacement du1 as this amount in direction 1 with original length dx1 also in direction 1. That's a linear strain. A linear strain, which in this case is going to be epsilon 1, 1, is a strain that produces a change of volume in the solid. And this is going to be very important later on, because, for example, fluids inside rocks, those affect the compressibility of the rock itself. Let me zoom out a little bit. And we can extend the same concept to the other directions, and therefore we're going to have epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3. All of those are linear strains. Okay? Any question about the linear strains? No? Let's go to the second one. Here, we're going to use a trick. I already have all the elements in the diagonal. So, diagonal elements are going to be 0. And in the off-diagonal elements, what I'm going to do is I'm going to add the symmetric term to du1 dx2. So du1 dx2, I have it there, but here I'm going to add du2 dx1. And the same as with this one, I'm going to add here, this one is going to be du1 dx3, and I'm going to add the symmetric term du3 dx1, and similarly here to, oh, there is a mistake here, right there, to du2 dx3, I'm going to add the symmetric term du3 dx2. And the other side is going to follow the same logic on the other side of the diagonal. All right. Let's finish with the math, and then we'll go towards the physics or why I do this. If I want to still hold this equality right here with the Jacobian, what I'm going to have to do is I'm going to have to subtract what I added. So in this case, in order to get still to 1 du1 dx2, I need to add the other half, and here I need to subtract what I added. So now the first row, second column element is this. And I'm going to do the same with the other two. du1 dx3 negative du3 dx1, and finally, well, not finally, I need the other off diagonal terms, but I have du2 dx3 negative du3 dx2. Okay, now the equality is okay. I add these three matrices and I will get this one, okay? But we need to do this decomposition because there is a very important meaning in doing this. And this is how we're going to get our strain tensor. Let's see what is the physical meaning of these terms over here. Okay, so similarly as we did for the previous case, let me draw again the initial undeformed cube, and to this undeformed cube I'm going to deform it in such way that the deformed configuration is going to look like this. What kind of stress do you think is going to cause such deformation? Shear. A shear, right? And if this helps, I'm going to add the shear stresses that cause this deformation. It's going to be stress here, shear stress there. They do add up vectorially and pull in this direction. There's another one here, and another one, oh, that's wrong. Another one in this direction. Notice the two pairs go clockwise, and these other two pairs go counterclockwise. When they combine, they produce this kind of deformation. Okay. So, let's see how these points move. Let's take a look at this one. This one moved an amount in direction 1, mostly. And this point over here moved in direction 2. Also, what we see from the figure is that the cube is not a cube anymore. Now it is distorted, right? And it is distorted by an angle, let's call it phi. And can you tell me what is the tangent of phi? Let me help you a little bit. For example, here, what is this length? dx2. And this length over here is dx1. So utilizing those lengths, what is going to be the tangent of the angle phi? Imagine this change of this angle is very small, okay? So let me du2 divided dx1, and we're saying this angle is the same over there, so it's equal also to du1 dx2, right? And what I'm going to do is I'm going to use that angle that tells me the amount of shear distortion in the solid in order to define the shear strain epsilon 1, 2. And that epsilon 1, 2, I'm going to say that this is more or less equal to 1/2 of 2 times, it's basically the tangent of the angle, tangent of phi, but I'm going to use these two, the numerator and denominator, to be able to use these two equations. 2 times the tangent of the angle is going to be du1 dx2 plus du2 dx1. So this thing is the same as that one. This is the shear strain, quantifies the distortion angle in the plane 1, 2. And this one is going to give me the shear strain in the plane 1, 3, and this one in the plane 2, 3. All of those are going to be shear strains. So I have linear strains, I have shear strains. Let's see what's going on with now this one. Before we do that, I just want you to notice that the displacement in direction 1 went to the right, and it was in the same direction as this one, so it was a positive displacement. And this one in direction number 2 also went up and went in the direction of the axis 2, so it was also a positive displacement. So these two are going to add up into a positive number. All right, let's see what this is now. We're going to draw again the cube. It's important to draw the direction of the arrows here, and if the initial size was that, we'll see now what is the change after. What's like this? Yes.
Stepping back just a minute. What's G?
G, where does it say G?
The E.
That one?
Yeah.
No, that's
B. What's right before it?
tangent.
Oh, TG.
It's a TG, it's a tangent.
Times the tangent?
Yeah.
Okay.
Well, but it's 1/2 of 2 times, so it's just a tangent.
Okay.
But I'm using here this tangent in a way that's going to be beneficial for the strain tensor because of the reason I'm going to show right now. We cannot use the Jacobian directly for what we're going to see right now. All right, so we could also think of a solid that it just rotates without any distortion angle. Although, well, let me, it should be something like this, okay? But this is in a straight angle, and the new one is also straight. It's just a rotation. In this case, I have a positive displacement in direction 1, but notice that now I have a negative displacement in direction 2. I shouldn't have clicked that. Okay. But it is very similar as before. This is dx2, this one is dx1, but now this is a negative change. And in this case, let's call this angle omega. The angle is going to be the same, but now when I do du2 dx1, that's going to be a negative term. Can you see that it's a negative term, this one? Because this is a negative quantity, this is positive, so this is going to be negative. So if I were to, for this particular case, if I were to add up du1 dx2 plus du2 dx1, that will give me 0. And that kind of makes sense, because when I add those two cross terms, they will give me strain. But if I change the sign right here, as we did in this case, that's going to give me a rotation. And a rotation like this one, it doesn't cause any strain. A rotation will be just a translation, right? I have this solid, and I can translate this length, but still is undeformed. And I can also rotate it, and still will be the same shape. It's not necessarily stressed. In order to capture strain, that's what we need to do with the Jacobian. We need to take away the rotational component. And this rotational component is this matrix over here, and this goes by usually omega, and it's called the rotation matrix. And these two over here just these two are going to be the strain tensor. And this is why we cannot use the Jacobian just by itself, but we need to do a few modifications to it in order to get the strain tensor.
Can you explain one more time how do you get from the du1 over dx to plus du2 over dx1 to the matrix?
Here?
Yeah, from the plus sign to the minus sign.
Okay, no, I didn't do anything. I just said that for this particular case, if I were to apply directly this equation, I'm going to get 0.
Okay.
But if I want to compute the rotation, let's finish this. What I have to do is I have to change the sign to whatever this second term is. In this way, if this is negative, negative and negative will be positive and will add up to the previous one and will tell me the rotation angle omega or theta in this case. But in this case, it's going to be omega 1, 2. It's going to be that component. So by changing the sign of the second component, I get the rotation. If I add the other term with just its own sign, I get strain. So here I have now the linear strains, the shear strains, and the rotation part, but I don't want the rotation in the strain tensor matrix. So summarizing then, in order to write the strain tensor, I'm just going to write now everything in a single matrix, but it's going to be the same. Let's put 60. I don't think I'm going to stay 60 minutes more, but let's just put 60. Here, strain tensor, then it's going to be equal to the linear strains and I'm going to put here also the shear strains. Okay, I think this is okay so far. And let's just complete this. I have a question for you. Do you think this matrix, this strain matrix, do you think it is symmetric?
Yeah.
Why?
Why not same terms?
The same what?
They have same terms.
You have the same terms, and notice that this term is the same as that one, but the order of the two terms inside parentheses is switched, but it's exactly the same. So this is also a symmetric matrix. It's a symmetric matrix, and these are strains. All of these numbers are derivatives of a real number with respect to a real number. So it's going to have all real components. If it's symmetric and it has real components, that's going to result in all eigenvalues which are symmetric too. I'm sorry, I didn't want to say symmetric. Eigenvalues which are real numbers. What would be the first invariant of the strain tensor based on what we see over here? And let me just complete this. Okay, so first invariant of the strain tensor. Let's use these components. So remember, the first invariant of any matrix
Isn't it the sum?
is the sum of diagonal terms. So in this case, it's going to be epsilon 1 plus epsilon 2 plus epsilon 3. Also, remember that any strain tensor can be written in terms of its eigenvalues, and the eigenvalues are going to be the principal strains. So same as we had principal stresses, now we have principal strains, epsilon 1, epsilon 2, and epsilon 3. And since the first invariant is going to be always the same, this is also going to be the sum of the principal strains. And one more thing, adding all those strains is going to give me what we call the volumetric strain. Notice that this is not divided by 3. It's not that like the mean stress that we had to divide the first invariant by 3. In this case, you just add up all of those strains and you get the volumetric strain. And the volumetric strain, by definition, is equal to the change in volume divided the initial volume. And it's going to be given by adding all the terms in the diagonal. All right. Just to close the loop about this strain matrix, we said it has real components and it is symmetric. But however, this matrix, the rotation matrix, it is not symmetric. If I write what this one should be for this component, you can see right away that it is not a symmetric matrix, because this number is a negative of that one. And because of that, this is something which is called a skew symmetric matrix, because the values in absolute number, they are the same, but the sign is different. As you look at it mirroring on the diagonal. Okay, let's see. I think we are done with this part. Yes, we are done. So what we just saw was the derivation of the strain tensor for small strains. And the final solution is that that strain is going to be sort of a Jacobian, a gradient of displacement as a function of position. And this is how we're going to calculate it, okay? Any question about this part? This is it. This is all we're going to see about kinematic equations. Similar as with the reservoir simulator, that you write your equations so you solve at the end for pressure. In mechanics, we're going to write our equations so we're going to solve for displacement. That's going to be our unknown. No? We're good? Okay, so then let's continue for 15 more minutes or so. Equilibrium equations, checked. Kinematic equations, at least for small strain, check. If you want to know about large strains, you can do a little more research on your own, or you can ask me about that. I'll send you some useful literature. The next thing is constitutive equations. And in a constitutive equation, what we want to do is we want to link stress to strain. All right, let's see how we do that. Okay, so let's rewrite what we had in the first page. We said this one was a function, stress is going to be a function of strain. And here, the first thing that we're going to do is a big assumption.
Which equations are which type of constitutive?
We haven't said which one so far. So we're gonna get there now in a bit. But the first thing that we're going to do is we're going to say that this relationship is a linear relationship. And this is very, very important, because when I assume linearity with this function f2, I say that, for example, applying f2 to an action A plus B is going to be equal to the summation of getting the results separately and then putting them together by a summation. Also, I can say that if I scale an action in amount C, for example, times A, this is equal to scaling the response C times after I apply an action. These simple equations that look kind of trivial, but they are not, are the basis of what are called a linear transformation, and allow us to use the superposition principle. Both in space and in time. And basically, we're going to use this a lot because probably we're going to say we have a very complex state of stress, and then we're going to divide it in several actions. For example, take a hydraulic fracture. On one side, we're going to say that there are in situ stresses, and we're going to solve that with one set of equations. On the other hand, we're going to say there is a hydraulic fracture, and we're going to solve that with other equations. But then we're going to add the two solutions together, like similar to this, and we're going to say that the solution of the entire thing is the summation of the two solutions. And that's only valid when you have a linear relationship. If you don't have a linear relationship, then this doesn't hold anymore. So, in that linear relationship, then, our sigma, our stress, is going to be linked through a coefficient that it's a scary one, because instead of now two underlinings, it's going to have 4. And you may say, what goes in there? We had enough with 3 by 3 matrices, and now I have something that appears to be even larger than that. You have a question, Bethany?
Yeah, is that a multiplication sign or a dot?
This is a matrix multiplication. And this new coefficient is going to be a matrix. We're going to see how it looks, but it's going to be a constant. So since it is a constant, this is similar to saying, for example, y is equal to b times x, where b is a constant. And since it is a constant and it's not going to change with time, it's not going to change with position, it's not going to change with all the actions that I add, this is going to be a linear relationship. This is similar to a linear equation. Okay, so,
Quick question.
yes,
But it does change with rotation, right?
doesn't depend. Well, now we're going to assume that this is an isotropic homogeneous solid, so it doesn't depend on location. We're going to relax that later on, and it will depend on location.
What about the rotation?
No, but we didn't get there yet.
Okay.
We don't have to assume that yet. It could change with rotation up to this point. Okay? All right, so let's try to reveal what is this C tensor. So in order to do that, let's first try to simplify a little bit our tensors. How many independent variables do I have in the strain tensor? Total, I know that it's a 3x3 matrix, right? So I have 9 values. The same for the strain tensor. But of those 9, how many are independent? We said that these are symmetric matrices, so independent, we're just going to have 6. Okay? If I were to do matrix multiplication, and here I have 9 independent numbers, and here I have 9, that means that inside this matrix C, there are going to be 81 coefficients. So instead of 1, as in this simple linear relationship with just 2 parameters, now I'm linking 2 matrices 3x3. So here I could have 81 coefficients. If I don't have symmetric matrices, but I do. So instead of 81, I'm going to have 36 independent coefficients in that matrix C. All right, so let's try to figure out what those 36 independent coefficients are. And in order to do that, I'm going to use something which is called Voigt notation. And the Voigt notation makes some of these operations a lot easier. And it consists in, instead of writing a tensor as a matrix, I'm going to write it as a vector. Instead of having a matrix 3x3, and since I know that I just have 6 independent coefficients, I'm going to write it as a matrix which is 6 rows, 1 column, 6 by 1. So what I'm going to do then is get, for example, a matrix sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 3, and let me just complete this one. And instead of writing this as a matrix, I'm going to write it as a long vector. And I'm going to follow the following convention. First number is on the top left, this one. And then the order I'm going to follow is going down the diagonal, going up this column, the third column, and finally getting over there. Okay? So it's going to be sigma 1 1, sigma 2 2, sigma 3 3. I like adding a line over there to separate normal stresses from shear stresses. Sigma 2 3, sigma 1 3, sigma 1 2. And those are going to be all the variables I have in the stress tensor. And of course, you know, I can all the time I can go back and forth from here to there. It's just a convention. But this is going to be very useful because we know how to write in paper a matrix 3x3. But this matrix C is actually a matrix 3x3x3x3, so it has like 4 dimensions. And there's no way to write that in paper. And that's why we need to to take to utilize this convention to make our life easier and to write this matrix C as a matrix 6 by 6. So that's what we're going to do. We're going to line up our stresses on one side and here I'm going to line up my strains on the other side with the same order, and here I'm going to have epsilon 2, 3, epsilon 1, 3, and epsilon 1, 2. And just by convenience, I'm going to add a number 2 over here. We're going to see where that number 2 comes from later on. But it's just a number 2. It doesn't change anything. All right. So now we have a vector which is 6 by 1 and a vector which is 6 by 1. Hence, the matrix that is going to be inside is going to be a matrix 6 by 6 with those 36 coefficients. When I relate stress to a strain and I'm multiplying the matrix times the strain, we're going to call this matrix the stiffness matrix, and it's going to go with the letter C, and each of these elements is going to be C11, C12, C13, C14, C15, C16, C21, and so on. For example, here I'm going to have C44, C55, C66, and this is going to be C61, C62, C63, C64, C65, and so on. But you get the idea, right? I have 36 independence coefficients C. So in the most general case then, if I want to link stresses to strains, I'm going to need 36 coefficients to characterize a solid or a rock. Okay, so fortunately for us, there are some physical rules that are going to allow us to figure out what some of these coefficients are, and they're going to be actually equal to 0. So let's see what the first one is.
Quick question.
Yeah.
The cross you draw in the stiffness matrix, that's no meaning, right?
The what?
The cross.
The cross?
Yeah, the cross you draw in the middle has no meaning.
No, well, the cross here, and that's what we're going to see right now. The cross, the lines here are meant to separate normal from shear stresses.
Okay.
The same as here, the linear strains with the shear strains.
Okay.
And the cross has the same objective.
Okay.
So we're going to see that there is something which is called shear decoupling. And what shear decoupling means is that a shear stress cannot induce a normal stress, or but let me write it. Let me write it because it's going to be clearer when I write it. Still, I have my same stresses here, and I have my elements over there, and here I have my strains. Okay, So let's induce or impart a strain epsilon 1, okay? So this is basically a linear strain in direction 1. And from this equation, let's say that all of these are equal to 0, okay? This one, that one, those are equal to 0. So if I multiply the matrix times this vector, in which, please don't write the 0 because you're going to have to delete it later, but I'm going to write it here. I'm going to delete that after. Let's say all of those are zeros. Then sigma 1, 1, sigma 2, 2, sigma 3, 3 is just going to be first row times column. Sigma 2, 2 is going to be second row times this column, and so on, right? So when we get to the shear part, the element here, which in this case should be C41, C41 times epsilon 1, 1 is going to give you the shear stress sigma 2, 3. So the question here is, can a linear strain produce a shear stress? So if you deform a solid like this one and you add a linear strain, can that produce a shear stress in a plane perpendicular to that, or in any plane? If you cause a linear strain like this one, can that linear stress produce a shear stress? Or let me even go a little bit further and more dramatic. If I add a linear strain, like for example caused by changing pore pressure or by submerging a solid into water, can that produce shear stresses? It cannot. In general, it cannot. And because of that, this term is going to be 0. And the same with all the other coefficients over here. And even if I had all linear strains which are not 0, there's no way that those are going to produce a shear stress. So all of these are going to be 0. And in the same way, if I have, or if I prescribe a shear strain, this is 1, 3, there is no way that that shear strain is going to produce a normal stress. So for example, when I get to multiply this row times this column, this element is going to be the one that multiplies this one times that one, and there is no way that by applying a shear strain I'm going to produce a normal stress. And for that same reason, all of these elements are going to be equal to 0. So let me write the elements which are not going to be equal to 0. Still, we have them there in the matrix. We got rid of already 18 coefficients. So now we have 18. Yes.
I don't understand because previously we said at first we had a 81 coefficient, right? And after finding the infinite coefficient with
36.
36.
Yes.
And now you are saying
18.
actually
18 because here you have 9. We already know what they are. They are zeros.
Okay.
And we have another 9 which are zeros too.
Okay.
So 36 minus 18, now I have 18.
Okay.
And I'm still missing this part. So because of the shear decoupling between normal and stresses and shear strains, we got rid of 18. This is what we just did. Now I have 18. Okay, I have 9 here and I have another 9 there. So 9 plus 9, that's going to be 18. Make sense or no? So here we have 6 by 6, 36, right?
Yeah.
Okay, but now I'm telling you that these matrices here, 9 coefficients and 9 coefficients, we know what they are.
Okay.
They are zeros.
Okay.
So 36 minus 18, now I have 18.
Okay.
And now I'm going to go to the next step, which is going to be the shear decoupling, but with shear versus shear. And let's do the same reasoning that we did before. If I have a strain in the plane 2, 3, I expect that that's going to be due to a shear stress in the plane 2, 3. So here I'm going to have an element C4, 4. But what about, do you think that a shear strain in the plane 1, 3, could that produce a shear stress in the plane 2, 3? Those two planes are perpendicular, right? If I have a cube like here, let's say, if I apply this shear strain, can this shear strain produce a shear stress in this direction? No, it cannot do that either. And because of that, these are going to be 0. And the same way, these are going to be 0, and these are going to be 0. So we got rid of 6 more coefficients, and now we have 12 coefficients.
Put that in terms of how you said, so you said linear stress cannot produce a shear strain.
Yes.
And then you also said application of a shear strain cannot.
In a perpendicular, cannot produce a shear stress in a plane perpendicular to that.
A shear stress
Yes.
in a plane.
For example, in our derivation of the shear strain, here we have a shear strain in the plane 1, 2. Well, this shear strain in the plane 1, 2 is not going to produce in the plane 1, 2 is not going to produce a shear stress in the plane 2, 3, or in the plane also 1, 3, 2. 1, 3 should be let's see, this one is like that, okay. 2, 3 will be like this one, and 1, 3 is going to be like this one. So you cannot produce strains by shear in a perpendicular plane. All right, so now we have 12 coefficients, and no, I'm doing my I have okay, yeah, I have 12, but there is one more thing that I can do over here. If this is a symmetric matrix or a vector, and this is also, we knew that it was a symmetric tensor. in order to conserve the symmetry, that means that also this matrix is going to be symmetric. So actually, these 3 over here, this one is going to be equal to that one, this one is going to be equal to this one, and this one is going to be equal to that one. So at the end of the day, I'm going to have symmetry. I'm going to have 9 coefficients. So C21 is equal to C12, and C13 is equal to C31. In general, this can be written as Cij is equal to Cji whenever I is different than j. So now I have 9 coefficients.
Can you repeat what the top right quadrant is all 0? What was the rule there?
Here,
Yes. What was the...
these are 0 because they mean that shear strains cannot produce shear stresses, cannot produce normal stresses.
Shear strains cannot produce...
Normal stresses, yes.
How would a strain produce a stress in the first place?
Well, probably it's easier to think on a stress producing a strain, right? You apply stress, you produce a strain.
Great.
But it is the same. Also, strains, if you prescribe a strain, that's going to require a stress, or it can also induce a stress. It is the same. You can go, they are interrelated.
Great.
Okay? We're going to see later on that we can switch the order of this matrix so that given a set of stresses, we can calculate the resulting strains, or as we have it right here, given a set of strains, we can calculate the resulting stresses.
Quick question.
Yes.
So in the middle matrix, in the lower left corner, those zeros is because normal string cannot produce shear.
This one?
Yes.
Yes.
The reason for that the 0 is because normal string
Because these
cannot produce
normal or linear strains cannot produce a shear stress. Correct.
And can you just repeat the lower right corner?
This?
Yeah.
So these are 0 because a strain in, for example, let's look at these two. A strain in the plane 1-3, shear strain in plane 1-3, or a shear strain in plane 1-2 cannot produce a shear stress in the plane 2-3.
Okay.
Okay? Alright guys, let me say a few more things and then we're gonna call it a day. But you have a question, Stephanie? No? Okay, let me tell you about how this is going to be useful for us. This matrix with 9 independent coefficients is what is called the orthorhombic model. And that orthorhombic model, it can help calculate stresses and strains for media that have different stiffnesses in different directions, and the 3 directions are different. For example, consider a layered,
Can you move up?
yes, consider a layered rock. And this layered rock, later we're going to play a lot with these equations, something that it's a new addition to this year in my class. I hope you appreciate it. is a sequence of soft and stiff layers. So, do you think that the stiffness in vertical direction is going to be the same as the stiffness in horizontal direction?
No,
Why not?
because rocks are weaker in tension.
Let's just disregard tension by now. I'm compressing this direction and compressing this direction. So the vertical stiffness, how does it compare to the horizontal stiffness? Where the dark ones are soft and the light ones are stiff. In general, the Young modulus or stiffness in vertical direction is going to be smaller than the Young modulus in horizontal direction. This is like a cookie, like an Oreo cookie, right? It's going to be softer in the direction where you have the cream than direction where they form the cookies. And it's the same with the rocks. But we're going to talk about that later on. In the orthorhombic case, there are going to be horizontal directions in which we also have different compliance or different stiffness. And that can be caused, for example, by a set of fractures. If I have fractures in a direction which are different from fractures in a perpendicular plane, a perpendicular direction, then the stiffness is going to also depend on which direction you're looking at. And in order to characterize this solid that has different stiffness in different directions, let's say E is west, different than the Young modulus in direction north-south, the model that you're going to need is the orthorhombic model. And if you want to measure the properties of such a fracture medium, and you're going to establish a relationship between stress and strains, you need 9 coefficients. V stands for vertical, yes. And remember, this axis is north-east depth.
And the lowercase n is that?
North-south.
Oh,
This means north-south, it means east-west, and this means vertical.
And then the one underneath that was the vertical.
This stands for horizontal.
Oh, that's an H.
Yeah.
Sorry.
But this case is without fractures. Now that we have added fractures, this may change. It's not going to be the same anymore. But in general, in rocks without fractures, if you just put layering, vertical Young modulus is going to be smaller than horizontal modulus. And that's why here I just put all of different, because we really don't know. Okay, guys, I think that was enough for today. And we're going to talk on Wednesday about an exception to the normal shear decoupling. And then we're going to talk about VTI media, vertical transverse isotropic. I'll see you on Wednesday.